Learning is the construction of lasting knowledge structures in long-term memory. This physical change in the brain's architecture dictates how a student handles every new piece of information they encounter. In any standard classroom, a student is bombarded by a near infinite stream of sensory data: the teacher's voice, the hum of a projector, the movement of peers. Yet, the human mind possesses severe processing limits. This diagram shows the linear cognitive pipeline incoming information travels through, from initial input into active processing, then storage. But it is vulnerable. When raw data hits the active processing bottleneck, the system can fail, causing information to bounce off and disappear before being understood. Effective instructional design requires strictly managing this pipeline. A teacher must control the flow of information through 3 specific mechanisms: attention, working memory, and schema construction. If an instructor ignores these physical tolerances, the system will overload. The mechanics of the brain dictate whether learning actually occurs, regardless of how interesting the lesson material might be. The very first node of this cognitive pipeline is the attention filter. Professional pedagogy often mistakes a physically quiet classroom for a learning classroom, but a student looking at the teacher is not necessarily processing the teacher's instruction. In this input zone, attention functions as an active, highly restrictive gatekeeper. Out of a massive wave of environmental data, it allows only a few targeted pieces of information to pass through to the processing center. Creating a need to know pulls this gate open. When a student's emotions are oriented positively toward a topic, it becomes physically easier for them to maintain focus on the specific data being presented. A humanities teacher can trigger this focus by engineering narrative tension or by posing an unresolved inquiry question that demands an answer to resolve the student's curiosity. A science teacher achieves the same result by connecting an abstract theory directly to a familiar, real-world phenomenon that the students have already experienced but cannot yet explain. Successfully hooking attention creates active engagement. This state is the mandatory prerequisite for any data to cross the threshold into the cognitive system. Once data passes the input filter, it reaches the second node, working memory. This is the active processing center where information is temporarily held and analyzed. This processing center possesses a strict physical limitation. Human working memory can only hold approximately 4 chunks of information at once. There is also a severe duration limit. Information in these holding slots degrades in seconds unless actively rehearsed. Cognitive load theory provides an instructional framework designed specifically to manage these 4 scarce holding slots. It identifies 2 distinct types of strain on the system. The first is intrinsic load. This is the inherent, unavoidable complexity of the new concept being taught. This intrinsic complexity occupies a fixed amount of available capacity, instantly consuming a portion of the working memory slots. The second type of strain is extrinsic load. This is the artificial complexity added by the teacher, such as distracting presentation slides. This unnecessary noise occupies the remaining vital capacity, filling the system with data that does not contribute to actual understanding. If the combined intrinsic and extrinsic load exceeds the 4 available slots, the system reaches a mechanical failure state. The bottleneck crashes, and the information is entirely lost. Teachers must ruthlessly eliminate extrinsic noise. Doing so ensures the working memory bottleneck remains stable enough to process the essential intrinsic knowledge. Successfully processed information finally moves to the last node of the cognitive pipeline, long-term memory. In stark contrast to the tiny 4-slot capacity of working memory, long-term memory operates as a practically infinite storage facility. Looking at this diagram, we see how the brain stores meaning here. It organizes knowledge into highly interconnected networks known as schemas. Within these expansive networks, individual related elements of knowledge act as tightly linked reference points, securing meaning through context. The brain uses these schemas to execute a biological workaround called chunking. Working memory pulls a complex cluster of information from a schema and compresses it into a single unified unit. This highly compressed chunk of data now occupies only a single slot in the working memory array, freeing up the other 3 slots for new tasks. Schemas operate as a cognitive software upgrade. They bypass the hardware limitations of the brain, allowing students to process vastly more information without experiencing an overload crash. To observe the mechanical efficiency of chunking in practice, we can examine the intense cognitive demands of evaluating a mid-game chessboard. When a novice player looks at the board, they perceive the complex layout exactly as it is presented, a scattered collection of independent pieces. As this visualization shows, the novice attempts to process every single piece individually. Tracking 12 separate pieces instantly overwhelms their strict 4-slot working memory limit. Now consider how an expert chess player views the exact same board configuration. The expert relies on a highly developed schema. This existing knowledge automatically groups the 12 pieces into recognized tactical clusters, compressing the data down to just 2 distinct chunks. By reducing 12 individual data points to just 2 chunks, the expert retains entirely free cognitive resources in their working memory to calculate higher-order strategy. Expertise does not increase the physical size of working memory. It builds robust schemas that make real-time information processing radically more efficient. Looking at the complete cognitive pipeline, it's tempting to view it as a strictly linear path, where information only flows forward from input to storage. The complete cognitive architecture is actually a circular system, where highly developed schemas in storage influence the input gate at the very front. What a student already knows directly dictates what their attention filter is capable of noticing in the environment. Consider how 2 different people process the exact same passing sports car. For a person with no automotive schema, their attention filter only registers generic, low-resolution features. They simply perceive a bright red car driving past. A car enthusiast possesses a highly developed schema, which enables the rapid, automatic clustering of specific visual details as the car moves. The enthusiast's upgraded attention filter immediately recognizes the exact contours of a 718 Cayman Porsche. This perception requires zero conscious working memory effort. This mechanical reality governs the classroom. A student equipped with a weak schema will literally perceive less of your verbal instruction and less of your presentation than a student with a strong schema. Effective teaching focuses on the architectural construction of schemas. These mental structures upgrade a student's capacity to perceive and process reality.